the purpose of really introducing the probabilistic modeling stuff in the morning was really to talk about a specific application of these kinds of models for text and analysis. Though what I'll present here is focused mainly on text document analysis. It really is broadly applicable. In fact, it can be extended in lots of different ways to capture lots of different features and sort of in a similar fashion to what we'll describe here, though we'll just sort of focus on the simplest model. This is sort of very much in the theme with the rest of the workshop, which is really focusing on text and data analysis. So before we do that, though, we need to build up a little bit, just a tiny bit more background on probabilistic modeling to sort of explain where this model is really coming from and why we would need such a model to handle these kinds of the kinds of data problems that we'll be taking a look at here. So we'll sort of have a brief discussion of what we call generative versus discriminative models, and I'll introduce latent variable models, which we haven't touched on yet. Then I'll introduce topic models, some of the assumptions that we need to make them work in practice. Then finally, explain a bit how one actually applies them and the algorithms behind them. The caveat with all of this is when it comes time for actual implementation, we'll be using a built-in Python library. In fact, most of your favorite programming languages will probably already have support for this algorithm, and I highly suggest that you don't code it yourself. It's one of those things that you can screw up and make it take years to analyze, because in this particular setting, we'll be interested in analyzing corpuses with millions of documents. So this is a time-consuming task. This is not that sort of toy spam email classification task that we started with. Okay, so by way of motivation, let's first talk a little bit about what I mean by a latent variable graphical model, or a probabilistic model. So sometimes in practice, the kinds of models we're interested in fitting actually have unobserved variables, and those unobserved variables are sort of intrinsically part of the problem. We never get to see their values, so we call them latent variables, but we know they're there. And in fact, it's really important that we know they're there for the modeling aspect of it. So I'll give some examples in a second. But the key part about latent variables is they are there. We can't directly observe them. Perhaps we can only indirectly observe them. So sort of the classic example of this is a particular probabilistic model that's referred to as a hidden Markov model. So unlike the Bayesian networks that we saw last time, I'm now going to distinguish between sort of two types of random variables. So random variables that have a sort of a gray circle, I'm going to consider those observed. And what I mean by observed is that they're actually part of the data. Okay? Random variables that occur with a white circle are latent. They're not part of the data set. We never get to observe them. So in a hidden Markov model, what we have, the way you should think of this Bayesian network is it's typically used to model time series data. So you can think we have a sequence of observations of some hidden process that we don't get to directly observe. This happens all the time in the sciences. In fact, this is the most typical use case. Almost every model that you encounter in practice actually has latent variables. So here's a good example. Suppose we wanted to estimate the average temperature for a particular year. So it turns out that there's a correlation between average temperature and how much trees grow in a particular year. So temperature and rainfall contribute to growth of trees. So we can't go back in time and measure the average temperature, 50 years ago. Right? But what we can do is cut down a bunch of trees and see how much they grew, right, over time. Right? So this is a great example of what we can't go back and observe these latent variables y corresponding to the temperature. What we can do is directly observe, right, the size of the growth rings. Other examples in engineering and the sciences, missile tracking systems, right? You can imagine you've got some radar system. They're noisy observations of some ground truth, right, where the missile actually is in space. You never get to really observe it. All you get are measurements of it. Same thing, you're running some physics or chemistry experiments. You typically get observations of some underlying process, right? And from those observations, you try to infer what the actual process is doing. So this is one way that latent variables come up in practice. Another way that they come up, which is actually more common, which we won't focus on so much today, but it's good to be aware of, is that oftentimes data has missing entries. A good example is with health records, right? We know, for example, that somebody has a temperature at every time of day, right? But nobody's health record has their temperature and blood pressure every second of every day. We know those things exist, right? But we only get to measure them, right, when the person's actually gone in, for an exam, right? So that kind of data is, those kinds of hidden variables are sort of partially observed, right? We get to see them sometimes, but we don't always get to see them. We would have to reconstruct the sort of the ground truth from our sort of partial observations. So dealing with latent variables is really, the typical fact of life, and it's in, the sort of models that we took a look at last time, like that's the supervised email classification problem, right? That's sort of more an anomaly, right? It's sort of a very fixed and special case, right? Real data has a lot of ambiguity and a lot of missingness, and other things that would need to be handled properly if we were to try to fit models to them. Okay. So the reason I'm introducing latent variables is that adding latent variables to probabilistic models gives you a lot of modeling power. And it's the kind of thing that we'll see really also allows us to give a nice story for how we sort of view certain probabilistic processes as happening. All right. But throughout this talk, you should really think of latent variables just like this, right? They're describing some underlying process that we can't directly observe, but we believe is actually happening. So when we talk about latent variable models, we make a distinction between two different types. Models of the two different types are discriminative and generative. So the difference is basically in the direction of the arrows. So last time we said that, the direction of the arrows doesn't really mean anything, right? Two things just means sort of two things are statistically correlated if there's an edge between them in the graph. Now when we have latent variables and observed variables, the direction of the arrows actually has some type of meaning. And depending on which way we put them, the models are better or worse for certain types of tasks. So in a discriminative task, the observed variables have edges to the latent variables, directed edges from observations to the latent variables. And in generative models, the arrow goes the opposite direction. It goes from the latent observations to the observed variables. And like I said, it looks like these two models are very different, but the type of probabilistic model they describe is somewhat different from a mathematical perspective, and it means that the two models are better or worse for different applications. So what do I mean by that? So in our discriminative models, right, as a Bayesian network, this thing implies that we can write the joint probability distribution of x and y as the probability of x times the probability of y given x. Whereas in the generative model, we have probability of y times the probability of x given y. Now, both of these, of course, can be used to describe the same joint probability distribution. But models of the top form are actually slightly better for situations where we actually want to solve a classification task, like we saw with the spam email filtering example. That's a classification task. We're really only interested in the probability of y given x. In such a setting, we don't necessarily need to model the probability of x. So thinking it back in this hidden Markov model example for a second. In this setting, we're really sort of jointly modeling the x's and the y's together because we're interested in the probability distribution over potentially over both the observed and the latent variables. In the naive Bayes model, right, where we had sort of label points to everything else, we don't necessarily care so much about like the individual probability distribution over the individual labels. It's sort of part of the model, but our real goal or our real interest is in predicting the label. And the same thing here, right? It depends on what our real goal is, what we're actually trying to predict, right? If our goal is to predict the latent variables, then which model we're talking about might make a bit of a difference. Okay. So which one of these we prefer in practice can be quite a computational preference, right? So like I said, if we're really just interested in predicting y, then the probability of x doesn't really matter, right? This is the probability of the actual observations, doesn't matter. So in this situation, we might just prefer fitting the probability of y conditioned on x to the data, right, and just ignoring this term. Right? We saw something similar, right, when we saw the Bayesian map inference rule, right? There, the denominator of that was the probability of the data. We didn't care, right, because it didn't affect the model fit for the parameters. Sort of same thing here. If all we care about is probability of y, we don't necessarily need to fit the joint probability distribution of both of these things. There's a lot of great examples where we absolutely prefer discriminative models. The generative model, however, sort of couples the latent variables together with the observations. And so it's not obvious necessarily how the generative model situations where the generative model might be preferred. But the name should give you a little bit of a hint. The generative model is actually better at generating new samples. You can see in sort of the picture in the left, the discriminative model sort of arise, the latent variables in some ways arise from fixed values of the observations. In such a situation, if someone gives you the observations, basically the latent variables don't matter, right? Whereas here, it's the observations arise from the latent variables, right? If you're given the latent variables, you can then generate, you could sample basically to get new observations, right? So which one of these we prefer greatly depends on the application. Discriminative models are better really for prediction, whereas generative models are better if we're interested in modeling a data generating process. So we saw some discriminative models. In fact, the lab you just did would be really an example of a discriminative learning task. We were actually interested in predicting the activities, right, at each time frame of the video. And in such a situation, we would prefer a more discriminative approach rather than a generative approach. Today this afternoon, we're going to talk a bit about generative models. And the generative model I'm going to focus on is something called Latent Dirichlet Allocation, because it has, it's a very strange and interesting generative model of documents, text documents in particular, that has a lot of applications. And as a side effect of that, it presents a very different way of thinking about fitting probabilistic models and the kinds of things we can do with them. So, like I said, we're going to build generative models for the problem of topic modeling. So the idea behind topic modeling, so unlike a supervised learning task, in topic modeling, someone just gives us a big chunk of raw data. We've processed it in some way, probably first. You'll get a flavor for what kinds of pre-processing we're doing in a second. But the idea is someone just gives us a chunk of data and says, tell me something interesting about this data. Right? So in machine learning parlance, we typically refer to these kinds of problems as unsupervised learning. Right? Someone hands you some data. There's no right or wrong answers. They're just saying, make some sense of it. So things you might be familiar with that fit into the unsupervised learning family are clustering. Right? So if someone gives you a bunch of data and you want to cluster it into different groups, that's an unsupervised learning problem. Topic modeling is very much like that. Right? It's you could view it as a specific type of clustering. And that's very much what the interpretation will be. The idea behind topic modeling is to discover somehow automatically the themes in your collection. So the motivated example I'll use throughout is, say we have a corpus of, let's say, newspaper articles. We'd like to divide them into topics, right? And now we could sit around here and come up with, OK, what are good topics for newspaper articles? Politics, sports, et cetera, right? But we'd like to automate this process, right? We don't want to sit down, right, with a collection of 1 million newspaper articles and figure out, like, what are the topics that describe these newspaper articles. We'd like to automate it. Once we sort of automate this process, we use our method for discovering these themes in the data to basically annotate the data. And once we have these annotations, we can use it to do other tasks, like search and summarize our data, right? So if someone says, I'm looking for newspaper articles about politics, right, we can return to them that subset of the data that we've annotated as politics. And again, the point here is this should all be done automatically. We won't necessarily know in advance that our corpus contains any information about politics. It seems a little bit strange how we could sort of extract this information without knowing what we're looking for, but hopefully that will become clear as we go along. So basically, the idea is like this. So we can imagine we have our collection of articles. So here, this is a science article, not a newspaper article. The way that topic modeling works is we're just given a big corpus of these articles. And we'd basically like to distill it into individual topics. So we'll do this in a couple different ways. instead of just assigning a single topic to each element of our corpus, we'll instead think of them as being a collection of topics. Right? This is actually much more reasonable in practice, right? An article about politics might also be about finance, right? An article about sports might also be about politics, right? And there's plenty of things that sort of cross over. It's basically impossible to write an article that's just about politics. Right? So we'll really view this topic modeling procedure as representing individual documents in our corpus of documents to be analyzed as basically a combination of topics. Now, the model that we're going to use to do this is basically a Bayesian network with latent variables. To really describe that Bayesian network, I'm first going to sort of describe the generative process that we're going to think of the way that documents are generated. Now, before I do that, with some caveats here, right? This is sort of a question that we had in the morning session as well. The generative model I'm about to present is not how people write articles, right? It should not be interpreted that way. In fact, it's very far from the way that a human would sit down and write an article. We're trying to somehow extract sort of high-level ideas about what kinds of things make articles similar in order to group them together. So here we go. So I'm going to describe first the high-level model, then I'll show you the Bayesian network that sort of captures this thing, and we'll talk about some of the finer theoretical details. So in order to really make any of this processing possible, we're going to have to make some really strange assumptions about the way text documents are modeled, basically to make the model fitting problem tractable at all. Our first assumption is going to be that the order of words in a particular document don't matter. So it doesn't matter, if you take your science article, you permute the words in any order that you want, we're going to consider it the same article. It doesn't matter. This assumption is what we call a bag of words model. Literally, like this document is just a bag of words. You can just pull the words out one by one in any particular order, and we'll realize that as the same document. Now, this is obviously a false assumption, right? So we actually saw something similar when we were looking at the naive Bayes model in the first lecture, right? Our features just said word in there or not. It said nothing about the order that the words came in, right? Or how they were related. Nothing, just there or not. Same kind of thing here. Order doesn't matter. It's just the words that appear in the document in any order. That's how we're treating individual documents. Our second assumption, which is also a little bit suspicious, is we're going to assume what's called a unigram model. That is that we're going to assume that in this big bag of words that makes up a text document, each word is drawn uniformly at random from some categorical distribution over words. Okay. Now, again, when you go to sit down to write an article, the next word you pick is not just drawn randomly from a hat based on some, probability distribution, right? That's not how people write things. So it's a gross simplifying model, but it turns out that, it works okay in practice. So when we put it all together, although these are, sort of gross simplifying assumptions, it seems to give back reasonable results. More generally, so here we're going to focus on the unigram model. More generally, LDA can be applied to more than just single words. So there's bigram models and trigram models, and you can anything up beyond that. There's good reasons to consider these other models. For example, there are some words that always appear together, or sort of phrases of words that that their meaning is as a whole is very different from their individual parts. So often there's some kind of pre-processing to handle that, or you want to go beyond unigram models. As you go beyond unigram, though, right, now you really consider word ordering, right, in the document, right? So you're sort of breaking down that bag of words assumption till eventually, right, if you just consider everything in order, you get a very good model, but it's overly complicated. It would be much too difficult computationally for us to actually fit such a model. So all of our documents are just bags of words each word is randomly generated from a categorical distribution. The last thing to specify is how we figure out what those categorical distributions are. So in general, we'll assume that what's called a mixture of unigrams model. So each one of our documents will first pick a topic, let's say Z. So come back to that in a second. And then it generates words from the document from conditional distributions like this. So conditioned on the topic that will give us a probability distribution over words, and we will sample a word from the appropriate topic. The reason we're considering it a mixture distribution is we'll treat every document, like I said before, as a collection of topics, right? Maybe about politics and sports and whatever, right? So it's not a single topic, it's a collection of topics. So the document itself is a mixture of these distributions. So for every word, we'll select some topic from that mixture and then generate that word randomly from the probability distribution over words for that topic. Okay? So in this particular framework, we're really going to think of topics for documents as probability distributions over words. So this is how we're getting around the fact that we don't know what the topics will be in advance. For us, a topic is just a probability distribution over words, right? So for example, a topic that might correspond to politics would have things like president and Senate and Congress and election, right? Those words would be very frequently occurring in that topic, right? Whereas, topics about, chemistry, would have things like atom and mole and, whatever, right? So, and you can see that those, as distributions, those two things are quite disjoint. There's very few chemistry articles that, talk about presidents and Congress and, right? And very few, political articles that talk about chemistry, right? So these topics are quite distinct. Some topics might overlap. That's okay. We'll kind of sort that out in the end. Okay. So I have a picture to illustrate that. Is everybody happy sort of with the process so far? Okay, good. So in pictures, it's always nicer to see a picture. So here's a document. So we're viewing each word in this document, right? And order doesn't matter. So the first thing we do is pick a probability distribution over topics for this document. So in this particular setting, I have 4 topics. Again, topics are just distributions over words, but I might think of this first topic, right, which is more of a yellow-green rather than a green. It's sort of hard to parse. Thankfully, there's no green in this document. So things like gene, DNA, genetic, we might think that this is a topic about genetics, right? So these are the most probable words in this topic. In this pink category, we have things like life, evolve, and organism as the most probable words. So this is probably like a topic about biology. Right? Green is brain, neuron, nerves. So this is sort of a topic about like, neuroscience. And finally, this sort of blue category has things like data, number, computer as its most probable words. This is sort of computation or computing as a category. Now, I did that verbally, right? It's sort of like by inspection. I looked at this probability distributions over words, and I attributed a particular topic name to it, right? The algorithm won't do that. It will just give us back the topics as distributions over words, and it will be up to us to infer like what that topic corresponds to. That sounds like it might be kind of a weird task, but in general, if you do a reasonable job with this approach, you'll find that you get kind of coherent-looking topics out of your corpus. We'll come back to a little bit of the details on that later. So what do I mean by a generative? What do I mean when I say that this approach is a generative model of text documents? Well, we first start with a probability distribution over topics for this document, right? So this thing looks like it's, I don't know, it's more yellow than pink than blue, and it's 0% green. So this is the probability distribution over topics for this document. For each word, I first select one of these topics uniformly at random according to this probability distribution. So for this one, I roll a die or whatever, and I got pink as my topic. Once I've selected the topic for this word, I just randomly select a word from the topic, right? Again, with respect to the probability distribution that's defined by that topic, right? So, for example, I got the pink. My random process selected the pink topic, and then I generated a random number and then selected life out of this topic. That's how we're imagining the documents being generated. Now, again, that's not how people write. Articles, but it's the way that we're envisioning the process working. Now, the point is that in this particular process, right, we don't know the mixture of topics for each document. We don't even know the topics, right, in advance, right? So the goal would be to recover all of these things. They're latent in this model, right? The only thing we get to see are the words in the document. That's it. right? Like I said, in this application, someone just hands you a big chunk of documents, and our goal is to make sense of them, right? And to discover, basically, the topics and the mixtures of topics that best describe the corpus. Okay? Now, this has tons of applications. Really, it does. There's lots of different applications where one wants to sort of extract high-level information from just a big chunk of raw data. So there's lots of text applications. You can use this for image applications too, right? Instead of words in a document, you can think of pixels in an image, right? Again, bag of pixels model would have them, we forget the ordering of the pixels, right? And we just try to build high-level characteristics out of them, right? So it's really broadly applicable. So don't think just text documents. You can really use this for a lot of different things. It's very good at extracting like high-level ideas, high-level topic concepts from data. Okay. So what does the model look like as a Bayesian network? So to introduce it, it unfortunately can't fit on a single slide. So I have to use some fancier notation. So this notation is called plate notation. The idea is every time you see one of these big boxes, there's a lowercase letter and an uppercase letter. The lowercase letter is replicated uppercase letter number of times. So what I mean by a picture like this is that, let's say, if k were equal to, capital K, were equal to 3, I would have a beta 1, a beta 2, and a beta 3. Right? That's what that box looks like. Replicate everything 3 times. Everywhere you see an arrow that crosses a box boundary, it's connected to everything, right? All the copies across the boundary. In this case, beta 1, 2, and 3 are connected to every copy of this inside WDN. All right. So let's break the model apart. So this part of the model is for the topics. There will be capital K topics in the model. Yep.
So with what you just said, it's not only beta 1, 2, 3 with WDN, but also ZDN?
No, because there's no edge that goes from beta to W. Does that make sense? The edges are replicated across the boundary, right? So when this thing crosses the n and the d boundary, it means a single edge here is replicated n times d times, because there's n times d w. That make sense? Right. So over here, this theta d thing is connected to zdn. There's capital D of these. Each one of them is connected to n things, right? N of these z's, right? Because it crosses the n boundary. So you sort of replicate them n times. So capital K is number of topics, capital D is number of documents, and capital N is the number of words in the dth document. Let's assume, so for simplicity, let's just assume we've truncated all of our documents to just single capital N, right? So there's just the number of words in each document is fixed. We don't need to make that assumption. It's just notationally for simplicity. Let's just assume that that's the case here. So what are we looking at? So you notice that there's only one sort of gray circle in this whole thing. So WDN here is an observed variable, and it corresponds to the nth word in the dth document. So there's these inside random variables, there's one for each word in every document. Okay. Now, of course, you would do some pre-processing. You're probably not going to, you'll probably throw away all the A's, ands, or thes, right? It doesn't matter. You did a little, I think in sort of some of the previous lectures, you did a lot of data pre-processing to throw this stuff away. Same thing here. Okay. The variables are connected in such a way that basically this model represents that generative process that I was just describing. So what do I mean? So you should think of beta k as a big long vector. It's a vector that has length a number of words, and it's a probability distribution over words. Right, so let's say, again, there's 10,000 words in the English language. You should think of beta 1 as being a 10,000 dimensional vector, beta 2 as being a 10,000 dimensional vector, beta 3 as a 10,000 dimensional vector, right, corresponding to the probability distributions over words for that topic. Okay? And there's capital K topics. On the other side here, we have theta d. So this theta d is the distribution over topics for the dth document. So theta d is a capital K dimensional vector, right? whose first entry corresponds to the fraction of topic 1 for this document. Second thing, entry is fraction of topic 2 for this document, et cetera. Right? So it's in our picture here, theta d represents this thing for this document. This is theta d. Whereas beta 1, 2, 3, and 4, right, are represented by these vectors. Finally, ZDN is the topic that we selected for the nth word in the dth document. Right? So for each word, remember that in the generative process, we sample a topic from this distribution. It gives us a topic for that word. And then we sample from this distribution, right, for whatever topic we picked to generate this word. Right? So the ZDN thing is the topic that we select for that word. And that's it. Right? All of these things are latent. Right? We never get to see them. We only get to see the words. Everything else we need to reconstruct by fitting this model to data. And we'll do that mechanism for doing that will be exactly the same as we did before, only the actual physical computational part is a little bit more challenging. Right. Questions about the model so far? Things that make sense, things that don't make sense. Okay. One thing that's worth pointing out is this model has both discrete and continuous random variables. So what do I mean? So theta d and beta k, right? They're vectors, but they're real valued vectors, right? Because they're probability distributions, right? So they're vectors of numbers between 0 and 1, and they sum up to 1. Z, right? The topic we select for each word, that's a discrete random variable. It takes one of capital K different values, depending on which topic you've selected. WDN is also a discrete random variable. It's basically an integer in 1 to capital V, where let's say capital V is the total number of words in your dictionary. So we've got 2 discrete random variables, and basically the remaining random variables are continuous. They're vectors of probabilities. So when we were talking in the last lecture, we were basically looking at discrete modeling problems in some sense, right? It was just heads or tails, right? Here we can have continuous things. The modeling problem is still the same. We'll have a conditional probability distribution, right? Going back from the picture, right? We have a conditional probability distribution of W conditioned on all of its parents in the model, which are the betas and the ZDN. One of which is discrete, but the rest are continuous. We'll need to parameterize the continuous distributions, right? We can't, for a continuous distribution, we can't write down its value for every real number, right? Instead, we'll need to extract high-level parameters, right? For example, a Gaussian distribution is described by a mean and a variance, right? Just 2 numbers, not like an entire continuum. So we'll apply the same thing here. The way we choose these probability distributions is the way that the algorithm gets its name. So the distributions of interest will be Dirichlet distributions. Those will be the distributions over these betas and the thetas in the model. And that's where you get the latent Dirichlet allocation. If you wanted different distributions, you could get a different name, right? Latent Gaussian, whatever, right? It depends on your application. The Dirichlet is great for these kind of categorical distributions. It's the generalization of the beta distribution to more than 2 alternatives. All right. So let's sort of dive in a little bit and talk about the details of how we're viewing the conditional probability distributions in this model. So like I said, the thetas and betas are going to assume that they're Dirichlet distributions. The definition of the Dirichlet distribution is right here. So a Dirichlet distribution over k random variables is a probability distribution over non-negative over k non-negative random variables whose sum is equal to 1. So we saw this with the beta distribution, right? It was a probability over 2 alternatives, right? They sum to 1, right? Think of it as b and 1 minus b, all right, for the coin flipping problem. This is the generalization. It's a probability distribution that's characterized by the choice of these alphas. You just take xi to the alpha I minus 1, right? In the beta distribution case, we only had two numbers, so it was easy. They had to sum up to 1, so the formula looked a little simpler. Again, this is up to proportionality. There's some normalizing constant here that we're just going to ignore. It depends on the choice of alpha and eta. as to what exactly the normalizing constant will be. So pictorially, the Dirichlet distribution is a probability distribution over probability distributions, right? Each different probability distribution is more or less likely depending on your choice of alpha. Just like we saw for the beta distribution in the coin flipping task, right? Depending on how you chose the alpha and beta for the beta distribution, right? It made certain biases more or less likely. Same thing here, right? Certain distributions over topics more or less likely depending on how you choose the values. Okay. So what does the joint probability distribution look like for this Bayesian network? Well, according to the factorization setup that we saw in the morning lecture, we know that the joint probability distribution over all the random variables, here I'm writing it conditioned on alpha and eta, right? Because those are the sort of the parameters of the respective Dirichlet distributions. It's written as the product, right, of each random variable in the model conditioned on its parents, right? So just back to the model really quickly, right? The beta k's don't have any parents, neither do the theta d's, but zdn has as its parent theta d, right? And wdn has as parents zdn and all of the betas, right? Because of the replication of those lines. So if we write that out, what that looks like mathematically is we have a product over all the topics of the probability of the kth topic. Right? We have a product over all the documents of the probability of that distribution over topics times the probability of the topic for the nth word in the dth document conditioned on whichever distribution over topics you selected times the product of each word conditioned on its parents, which are the topic you selected for that word, and the whole set of topics. So in order to talk about model fitting, we need to specify what form each one of these conditional probabilities is in. From the previous slide, we just said that these probability distributions, the probability distribution over beta and theta, those will be Dirichlet distributions, right? Whose parameters are eta and alpha, respectively. The other probability distributions we have to pick. So the probability of zdn conditioned on the topic distribution, right? So what we're asking is, what's the probability that you pick a specific topic, let's say zdn equals 1, conditioned on this distribution over topics? Right? Well, this is the probability distribution. So the probability that zdn equals 1 is just the first entry of this vector, right? Whatever it happens to be. Right? The probability that zdn is equal to little k is just the kth entry of this vector. And that's what I'm notating up here. Same thing for the words, right? We know that each word, once you've selected the topic, right, the words are generated by sampling from the probability distributions over words for that topic. So the probability that the nth word in the dth document is equal to little v, conditioned on z and all the betas, well, we look at which topic we picked, which is v. We look at that entry of the topic determined by z. Right? So if we had selected the first topic, we would look at beta 1, its vth entry. That tells me the probability of selecting that word. And that's it. So that fully specifies this model. Right? Now, the trick is that we would like to fit this model to data, but it's a little bit more complicated than our previous maximum likelihood estimation approach. So the reason for that is that in this particular setup, we're never given values for z, theta, and beta, right? Our data only consists of the words, right? We don't get to see anything else. Right? So to do maximum likelihood estimation, right, our maximum likelihood estimator should really compute the probability of w, right? So we'll have to compute that from this quantity. And that's where all the hard work is in this LDA application. OK. Let's pause there again for questions. So we could really stop here and we could just go right to the lab, and you could just try it out and see. Right? Well, I'll give a few more details. I want to go a little bit, though, into the theory about like how we actually do this, because it's sort of important from a practical point of view, like how is it that we will actually fit this thing to data? It turns out we can't do it exactly. This turns out to be an NP-hard problem. It's intractable, unless some theoretical things we believe not to be true turn out to be true. So we don't expect to be able to solve this problem exactly. So in practice, we have to make approximations for it. So really what the algorithm that ends up doing this is sort of like an approximate maximum likelihood estimator, which could be exact, but in practice tends to not be. And that creates some difficulties for actually fitting these models in practice. And unlike sort of the maximum likelihood estimation problem where we basically took a derivative and solved it exactly, now what we end up with might not be the optimal solution. We might have to run this procedure a couple times. So we'll talk about that in a little bit. Any questions about it? Good. All right. So before we sort of dive into the technical details, right, we should ask, like, how reasonable is this model, right? Like, when I was describing it, it sounds actually quite unreasonable, right? I mean, we're making really a lot of assumptions about the way that documents are generated. It turns out that these assumptions, although they are not exactly the way that humans generate documents, I would argue that they're actually quite reasonable in practice. The reason is that we don't really expect our corpus to contain sort of any like sort of deliberately misleading documents. By that I mean that the corpus is likely to be like legit, real generated text, right? We're not assuming that there's some adversary that just populates our corpus with like random gibberish, right? That might really mess up something like this, right? So under the assumption that like these are sort of like legit documents, right? It seems somewhat reasonable to think that this model can extract at least some high-level topics, right? How good it is really depends on how it performs practically, which I'll give like just some brief flavors for, and then you'll get to try out more in the lab. But I really want to emphasize that like if you want to go, so you can extend this model a bit, but as you add more and more realistic assumptions, it becomes more computationally intractable to actually do this. Right? As it is, it can take, even with like high performance computing on large corpuses, it can take hours or days to actually, extract the topics. That's not necessarily a problem, right? We kind of view that we're going to do this like once. You're never going to do this again, right? You're going to annotate your corpus, extract the interesting topics, right? And probably not do it again, right? Unless you sort of have, your data is continuously increasing. It's really useful, in fact, in the social sciences. So I have a lot of friends in the humanities that have used this for all sorts of things. So the model can be extended in really interesting ways. So I have a friend from grad school who studies Chinese literature between some X time periods, right? And so China has a very rich history, and part of the difficulty with very long histories is that it's very difficult to attribute authorship to documents, right? We've sort of lost who wrote things. We have like lots of ancient texts. We don't know who wrote it. Slightly tweaking this model, instead of asking for it to extract topic information, we could ask this to create distributions over authors for each document. We can try to attribute authorship in individual documents. And it turns out that does quite well. And imagine some poor humanities student who has to look through millions of Chinese documents and writes a whole thesis just about who they think wrote document X. Right? This is a way to sort of streamline that process, right? And pull together sort of high-level information that might be really useful for identifying authorship. One more caveat with authorship, just as an example. So when we were talking about how one might prune the data, right? You got rid of the a, ands, and thes. If you want to analyze authorship, you should probably keep them in there because the number of definite articles that somebody uses is a great way to identify, who wrote the article. So I think people have actually done this for scientific papers. So for small collections of like NIP submissions, you can get a feel for which author of the 8 authors on the paper actually wrote it by doing these kinds of high-level extraction. So there's really a lot of application of this, and when you think about where can I apply LDA, you should think at much higher level, like just the idea of like extracting high-level topics from some kind of corpus that's sort of a really broadly applicable thing, right? It's not really restricted to just magazines or newspaper articles. It's really a lot of things. Okay. Oops. All right. Okay, so let's talk a little bit about the theory. I'm going to try not to bore you too much with the technical details. Like I said at the beginning, this is not really an algorithm that you would implement yourself. I think my students are not in the room. So my students have implemented this at very different times and screwed it up a number of times. I can say that because they're not here. It's quite tricky. This is not the kind of thing that you want to sit down and write yourself. Right? It's really nuanced. It's very easy to screw it up. You mess it up in one place, it can take you weeks to figure out where the bug is in the code. That's a problem with a lot of these optimization procedures, right? For a very complicated model, you have one bug in your derivative somewhere, and it can take you weeks to figure it out, right? So ideally, you don't implement this, which is great because there's lots of standard libraries to do it. But I think it's a good idea to have sort of a little bit of a feeling for how these things works. One, because it will help you understand some of the nuances of the algorithm, like how should you interpret its results, right? How confident should we be in what it gives us back? But also, it gives you sort of an appreciation for why this is actually a somewhat hard problem, and it gives us just a tiny glimpse into the kinds of methods that need to really be developed, or that we are developing, to handle like really large-scale data processing from a probabilistic modeling point of view. So the algorithm I'm going to describe, like at a somewhat high level, we're not going to take the derivatives or anything. Is based on what's called variational EM, and I can explain why you need to do that. It's sort of a very high level. When we, for example, did the coin flipping problem, right? We wrote down the log likelihood, we took a derivative, we solved, we got an answer, right? That answer was the right answer, and we were done. Like I said, though, the difficulty with this particular problem is that what we would really like to do is maximize the probability of this collection of words, right, conditioned on the parameters of the Dirichlet distributions. Right? We don't get to observe anything else. Those things have already been eliminated from the model. So in a probabilistic setting, right, how do you go from sort of a joint probability distribution over random variables to basically a marginal probability distribution? You do that by summing or integrating out the remaining variables. So if I want to compute the probability of W conditioned on alpha and eta, I can look at that joint probability distribution that we wrote down, and I can integrate out over theta and beta, and I can sum over all the different possible z values. Right? That's how we compute the marginal probability distribution. That's literally the definition of this object. You can see why this creates a bit of a headache automatically. I'm not going to write it down, but let's just say we tried to take the derivative of this thing, right, with respect to theta or beta or z. Right? Well, z is discrete, but let's say theta or beta. Right? Unlike before, where we had just a term that looked like that parameter times log, like something times log of that parameter. Now the log of a sum is 1 over the sum times the derivative of the sum. It's some messy quantity, right? It's not nice. It doesn't have a closed form solution. And even worse, like it actually might be that the integration is not tractable. So there's other issues here. These are really high dimensional integrals potentially, right? We're integrating over probability distributions over 10,000 words, right? So these are not low dimensional. They're not low dimensional integrals. Approximating high dimensional integrals is a huge pain and is the subject of lots of work in numerical analysis. So we'd really kind of like to avoid that if possible. So the trick that's used basically in most of what would be called like the variational statistics community is to introduce what we call a variational lower bound. So it's a cute little trick. The idea is that I want to turn sort of this intractable integral, I want to approximate it in such a way that I can actually compute some of the resulting integrals and the resulting quantities. So the trick works like this. I introduce a fake distribution over z, theta, and beta. So here I'm calling it q. I multiply and divide by it. So let's make the assumption that we'll only do this where this probability distribution is non-zero. Everywhere else we'll just assume the q is 0 and not multiply and divide by it. So no weird mathematical trickery here happening. Just multiplying and dividing by the same number, they cancel out. Okay. To get a lower bound on this quantity, which will actually end up making things tractable to compute, after one additional assumption, we'll apply what's called Jensen's inequality. So I'll write it down in a second, but before I write down the general form, Jensen's inequality tells us when we can pull basically sums through logs, or more generally, sums through convex or concave functions. And when we do that, we get an inequality. So in this particular case, log is a concave function. So the general theorem I have on the next slide says something like the log of an expectation is at least as big as the expected value of the log. Right? So the expectation here we're viewing as it's the expected value of this ratio with respect to this probability distribution. Let's say Q is a probability distribution. And so we can get a lower bound on it by doing this. So general theorem, something like this. If you have a concave function that takes in an n-dimensional vector and gives you some real number back, and you have a collection of capital M different n-dimensional vectors, and a collection of coefficients that are in the interval 0, 1 that sum up to 1, then if you apply that function to basically the average, the weighted average of the x's, it's always at least as big as the weighted average of the function applied to each of the individual x's. So we interpret this, in a probabilistic setting, right? You can think of the lambdas as the probability, right? Probability of like x1 in this case, right? So this is sort of like an expected value. This is the function applied to an expected value is greater than or equal to the expected value of the function. And that's basically what we're using to derive this lower bound here. It looks like we might not have made a lot of progress because it actually looks like I made it worse. I introduced some new distribution that conceivably I have to optimize over because, right, different choices of Q might give different lower bounds. I'd probably like the tightest lower bound, right? So I've made the problem more complicated. It turns out, though, that this particular formalism decouples the problem in a nice way. Under some sort of simplifying assumptions, it breaks it into sort of two pieces: a piece that looks like Q expected, a sum over Q log Q, and a piece that looks like the sum over Q log P. The final step to make everything tractable here is that I'm going to assume that Q is actually an easy distribution, right? Easy in the sense that it will make the integrals tractable. It of course will give me a strict lower bound. That won't be able to be necessarily attained in practice, but it'll make things computationally possible. This is a good thing to keep in mind. There's a lot of different methods in probabilistic modeling that basically apply the same technique. This is just a very generic technique. You've got an expected value of a log of an expectation, and you get lower bounds by basically switching the order of the expectation and the log. We do this actually a lot in the machine learning community. There's a lot of different machine learning algorithms that are basically built on getting nice lower bounds like this for which we can actually compute. Now, right, again, the caveat with all of this is that we're necessarily going to make this tractable, we're necessarily going to introduce approximations, right? So now the answer that we get from this is not exact, right? There's no like one answer that this thing will converge to. In fact, it's not too difficult to show that this optimization problem over theta, beta, and z it's not a convex or concave optimization. It's not a nice optimization problem. There's not a unique solution. This is the space of the function space of this thing. It has lots of peaks and valleys. It's a very complicated looking thing, right? Again, to connect with some other things that you might have experience with, right? Same thing with neural networks, right? That's not a concave optimization problem, right? The optimization problem doesn't have a unique. It might have a global optimum, but there's lots of local optimums. And part of getting neural networks to perform well, right, is regularizing and coming up with techniques to sort of help it stay out of poor local optima. So same kind of thing here. All right. So just a few details on that. We'll wrap up, and I'll show you some examples of what this sort of looks like in practice. Okay. So, first observation is that the way this algorithm will work is we're going to try to maximize this lower bound with respect to Q. That will give us some solution. We can treat, it turns out that this inequality is an equality under the optimal choice of Q. There is some choice of Q that makes this equality. We'll introduce an approximation which will prevent that from happening, but there is one that makes this tight. if we had such a thing, right, if we could find that thing, it basically gives us the joint probability distribution over z, theta, and beta. If we had that thing, we're done with this problem. Why? Because someone's given you the distribution over z, theta, and beta. If you want to find the parameters that maximize the likelihood, we just choose the things that maximize this Q function, right, just by itself, right? It's sort of acting as a surrogate for this big distribution. We'll see that in a little more detail in a second. However, like I said, to make this work, we're going to make some assumptions about the Q distribution. So a typical trick in, well, just machine learning and probabilistic modeling in general is to, when we have these kinds of variational optimization problems, so the term variational is a little bit overloaded. In a machine learning context, when someone says variational optimization, what they mean is an optimization typically over functions, right? So here we're optimizing over probability distributions, so we call it a variational method. They all basically have the same form. They're optimizing over some lower bound generated by some kind of expectation. A common assumption that people make to actually make the computation work is we'll assume that the approximate distribution Q has this particularly simple form. One simple form that's very popular is something called a mean field assumption, where we assume basically that this joint distribution over z, theta, and beta is really like a product of separate distributions over each of the components by themselves. This is called a mean field assumption in sort of probability parlance, right? When you have a probability distribution that has this property, right? All of these random variables are independent of each other, right? This is sort of the definition of independence. If you have a probability distribution over A and B, and the probability of A and B is equal to the probability of A times the probability of B, it means that A and B are independent. So this mean field assumption is nothing more than just assuming that each one of the variables of interest here is independent. That's particularly nice, actually, if we look back at this lower bound, because if we put this product in here, multiplying it by the log, we can turn these sort of high dimensional integrals into lower dimensional ones by just integrating against the quantities that one at a time, basically, because of the independence assumption. We'll write it out in more detail in a second. Okay, so then our new optimization problem then is to find the choice of these distributions, right, that maximize that lower bound. Again, it won't be tight. This is not the optimal solution to that problem is given by the probability of z, theta, and beta conditioned on w, right? We will not. That thing does not exist here, right? We don't have that thing. It's certainly not going to be of this form. So the optimal solution to maximizing the lower bound with respect to this assumption will just be an approximation. Despite that, though, it's relatively easy and computationally efficient enough to actually run on relatively large corpuses. Before moving on, questions about this? Good, everybody's happy. Hopefully straightforward. Now, like I said, the actual nitty-gritty details of implementing this is super tedious. So in the spring, I usually teach a probabilistic models course here, and at the end of the semester, the students are asked to basically apply the techniques from the class to like a data set or a topic of their choosing. And every semester, I get somebody that wants to do LDA, and they decide they want to implement it from scratch, and then they get to their presentation, and then the presentation is basically it was a disaster, like nothing worked. I really just want to emphasize that, like, yeah, it's tricky to get right. Even though like conceptually it's not difficult, like practically it's easy to mess up. Okay, so what does this look like in terms of the problem we're trying to solve? So we've got our likelihood. We take the log. We get this lower bound, right? We introduce this approximate distribution Q, and we maximize the lower bound over these Q functions. Right? Now, the way we do that, again, the details are super boring, so we're not going to write them out. We literally just take the derivatives with respect to these quantities, right? Just like we did before for the maximum likelihood problem. It turns out they are not super complicated, but there's no closed form, right? So the typical way to handle an optimization problem like this, where there's no closed form, is to do some kind of iterative optimization strategy. So the most popular one, I think, that typically is employed here is stochastic gradient descent method. So right, we compute the derivative, we look at the direction of greatest increase, we step in that direction and just repeat, right? Eventually this thing will converge to like, under mild assumptions, to a local optimum, right? That local optimum is basically what we return. We'd love it if it can converge to the global optimum, but like I said, there's no guarantees here because, this function has lots of peaks and valleys, and if you just step towards the direction of the greatest increase, you might end up at a local optimum, not a global optimum. Okay. All right. So once we've done that process, so for a fixed alpha and eta, we can do this process. It gives us a Q back. That gives us an approximation of the conditional probability distribution of theta, beta, and z conditioned on W. From that, we can use that to estimate the optimal z, theta, and beta, right? We just look at this Q function and say, okay, I'm going to maximize the pieces separately. It's easy because they're all independent here, right? So looking back at the factorization, right? This is a discrete probability distribution. I want to find the optimal choice for topics. I look at this discrete probability distribution over the topic for the nth word in the dth document. I just select the biggest value of z, right? It's independent of everything else. I just pick the best one, right? Same thing for the thetas and the betas. They're all independent. I just pick them all separately. So it's just a bunch of separate, easier optimization problems that I just solve for. And that's it. So the full procedure, actually, the actual variational EM algorithm would then do one more complication beyond this. So it would also try to select the best alpha and eta. So we would find the best lower bound. We would use that lower bound to approximate the derivative with respect to alpha and eta. We would then do one step of stochastic gradient descent for alpha and eta, and we would repeat. So that's the variational EM algorithm, right? For a fixed alpha and eta, though, it's just basically maximizing this bound to get an approximation of the quantity that we're interested in, right? And then just maximizing the individual pieces to figure out the answer. Okay? Yeah. So conceptually, not so bad. Practically, kind of annoying, but conceptually, really not so bad. Good. Any questions? You guys are way too quiet. After lunch, I was expecting more energy from this crowd. Okay. Okay. So let's take a look at like what you might get running this algorithm in practice. So like I said, you'll get to try this out on the lab by yourself. But here's an example of like what kind of topics you might get back from a sample LDA run. This was done on newspaper articles.
So let me ask a question. So from my understanding, so K is arts, budgets, children's education, right?
Yep, K is the number of topics you would like it to find.
So, well, from my understanding, when you said we have to choose the topics.
So, right, so the algorithm chooses the topics as distributions over words, but in advance, you must specify how many topics you want. Does that make sense? It's a good question. I was about to talk about it anyway. Where's the model? There it is. In this model, you'll note, right, like how many of each of these random variables, right, is determined by these quantities n, d, and k, capital K, right? So here, capital K is some fixed number. It doesn't change throughout the algorithm. It's fixed. So capital K tells you how many topics you have, or you want.
In the algorithm, it tells you. So you run and say, you want.
Right, you run the algorithm, you have to specify capital K.
So
You choose capital K, right? The algorithm will then decide, the probability distribution over words for the topics, right? But you specify how many you want. It's really important, it's actually a really important point that's worth emphasizing is that you don't know how many topics there are in advance. It's just not possible to know. Sort of by analogy with clustering applications, right? If someone gives you a bunch of data and says cluster it, you also don't know how many clusters there are, right? And what's a good clustering, right? What's the right number of clusters is very much up to interpretation, right? So, depending on what your application is, if K is relatively small, or you think there's a small number of topics that you're really interested in extracting, you might just do this by inspection, right? You run the algorithm a couple times with different values of K and look, what do the topics look like that I get, right? Once you sort of start getting like kind of nonsense looking topics, you might say, okay, that's sort of beyond what I'm looking for. There are other ways to sort of pick K in a more methodological way. You have to be really careful though. So in this model, if you say we start off, we do this thing. We run it with K equals 4, let's say. And then we run it again with k equals 10. It's not necessarily a good idea to just look at the value of the likelihood, right? We could do that, right? That's the thing that we're optimizing. We could look at what's the value of the likelihood. But the problem is that with larger k, technically, you can always get a higher likelihood in some sense, right? Because, right, you could just set some of the topics, you just ignore them, right? Right? That, let's say theta d always sets topic k with probability 0. So then that's like having k minus 1 topics instead, right? So the increasing k, the models sort of, they sort of contain each other. The flip side is, though, because this thing doesn't give you the optimal solution, it's at some local optimum, you might not, it's not clear what you'll get, right? It might converge to something that's better or worse. It really depends. You might have to run it a couple times. There are other ways to assess basically model fit here. So sort of the standard way to evaluate basically model fit in practice, right? The way that you should do this, I don't forget this machine learning application for a second. For any machine learning application, right? When you have some parameter that you're trying to tune sort of separately, and you want to figure out how to choose it, the right way to do that is to hold out some of the data that you're training on, hold it out, and then evaluate the model fit on that held out data. Like how representative, like how well does the model that you fit describe the data that you didn't train it on, right? So the same thing is true here. There are different metrics for that evaluation. I think that one of the more popular ones is something called perplexity. In this case, it's sort of it's an interesting way to look at the log likelihood, sort of a mix of log likelihood and some other things, to evaluate like how good is the model fit, right? The log likelihood tells you a little bit of the story, right? But if you're not looking at sort of on held out data, right, it only tells you sort of part of the story. So you should. Ideally, in practice, you should hold out some of the data to do this evaluation, right? And if you did that, you could look at how good is the fit with different values of k on the held out set, right? And then just select the value of k that has the best fit on the held out set. Yeah. It's another thing that's worth pointing out with these sort of latent variable learning problems, right? There's no necessary ground truth answer here, right? I mean, we're extracting patterns from data. There might be lots of different patterns that are sort of equally good descriptions of this thing, right? There might be lots of ways to decompose the corpus into k topics that make sense, right, and are reasonable and give a good, likelihood fit, right? So, lots of caveats here, right? You don't necessarily get back, there's no kind of clear right answer. So, it takes some interpretation. You need to probably look at the data, use some held out data to evaluate. But yeah, absolutely, k should be picked in advance. There are, more generally, so that there is research on methods that would be called like non-parametric methods. Non-parametric methods would not require you to specify k in advance. It would be sort of part of the learning strategy. It makes it even more complicated to implement. In practice, I don't know. It really depends on the application you have in mind as to whether or not you really need to do that. If you're really trying to extract a small number of topics, you might be able to get away with just sort of inspection. To get something meaningful. If you're really trying to extract a large number of topics, right, you might need to use one of these other methods because you don't want to hand look at 40, 100 topics, right? It's too much to process. Okay. But yeah, great question. All right. So then here's in this example, right, it was run on newspaper articles, and we set capital K equals to 4. What you see here is the topics that were returned by the algorithm, right? So we ran the method. So here, I believe this was the full variational EM. So it picked the alpha and the eta, and then iteratively maximizing that lower bound. And again, the most so words in the top words in each of these columns are ordered from most probable to least probable. We can look at what we get at the end, and like I said, we can, just like we did sort of when I was describing the algorithm, we can sort of assign names or meanings to the individual categories, right? So this first category with like new, film, show, music, movie, play, musical, best, actor, right? This sounds like it's a category about the arts, right? Same thing here. This second category is million, tax, program, budget, billion, federal, right? It's something about fiscal, government, something, right? So I mean, generically, you might say budgets or like fiscal management or finance or something. Categories like this: children, women, people, child, years, families, right? Might be about children or families or family life, right? There's no there's no right or wrong answer here, right? We're just sort of ascribing a name for the topic.
These are just post hoc
These are post hoc human adaptations, right? But in some ways this is important, right? Because we don't know what the topics are to begin with, right? We're sort of asking for that information out of the algorithm, right? So this is just sort of us retroactively saying, okay, well, this one looks like a topic about X. Really, this process can still be useful. After you run the algorithm, right, you can see sort of what it thinks like are the best descriptors, the best ways to sort of split the documents up, right? And sometimes you can get really surprising things, that you might not have expected. Sometimes surprising in a good way, sometimes surprising in a bad way. So if it's surprising in a bad way, you probably need to adjust K a little bit or just rerun the algorithm. Okay. All right. So that's an example of what you might get back from running the algorithm on this data set. Also, right, so the algorithm gives you back everything, right? It gives you back the choices, it gives you back Z, theta, and beta, right? So we can also use the values we get back for Z to annotate the documents, right? So here, again, it's kind of hard to see in these lighting conditions, right? I've taken one of the documents and I've annotated the words by the topic that the algorithm thinks is most probable for each one of the words, right? So again, like the green one was about finance. So like, right, you see money and fund and grants and services, right, and foundation and president, right? Those things like get a green color, right? Whereas like New York Philharmonic and performing and Lincoln, right? Although we probably should have Lincoln Center. This is a great example of a bigram, right? Lincoln and Center by themselves are two different things, right? In fact, they get put in two different categories here, though I think we would all agree that Lincoln Center belongs in the arts category, right? So that's it. So what we get back here really is sort of an annotated corpus, right? And we can ask like how much of this document is about the arts? How much of it is about finance, right? These are things that we can extract, right, after we've, in sort of a post-processing step. An application, so to sort of bring this back to like, how might you apply something like this in practice? A good example might be the following. Let's say like I'm a grocery store chain, right? And what I have is lots of data about customers and what they purchase on each trip. So let's think of our documents now as the receipt for an individual, right, when they went grocery shopping, right? What I'd like to do is extract trends from this, right? Because I want to be able to put the milk next to the bread, right? If people who buy milk buy bread together, but I don't know how to classify people, right? Like I'd like to extract like the most, quintessential types of people that shop at my store, right? And I don't know how to classify them in advance, right? So I can really represent people then as probability, like the topics here are probability distributions over items you buy in a grocery store. And like different individuals are more of one topic, right? They're more of one type of shopper than another, right? I can use this information. So once I do this as a pre-processing step, I can then use this as part of a supervised learning method, right? To try to fit users to products or services that I'd like to sell, right? This is also the same kind of thing that you would see with like a clustering thing, right? Usually it's the first step of some machine learning process, right? Where you divide things up and then you use that, to fit some other algorithm, right? But the first step is really important because you don't know how to break the data apart into interesting subgroups to then do further processing, right? Because there's no labels. We don't know that that shopper one, loves, shopper type one loves, milk and cereal. I mean, we don't know, right? We want to break them apart, right? Yeah. And this is, in fact, these are the kinds of things the kinds of applications that LDA is really useful for. Okay. Sure. Yeah, again, it's kind of like one of these like by inspection things. So it typically helps if you have a further application in mind, right? So let's say we did want to solve this shopper problem, right? So we have something like I want to maximize profits or something, right? And I can break things down into different shoppers, and then I can fit a separate model as a second stage, right, to solve some supervised learning task, right? So then I could say, from the topics I've learned, which one best solves the supervised task, right? If that's what I'm really interested in, that's probably what I should use as my metric for selecting K, right? But it really depends on what you're trying to use it for, right? If it's just sort of trying to get a feel for data, right? Like, someone gives you some new data set and you're trying to get a feel for it and you like want to know like, what is it kind of composed of? Just for your own purposes, maybe you don't need, maybe you just sort of do it by inspection, right? If you have a specific task in mind, I would base it based off of whatever performance metric for that task that you're trying to solve. It's not so bad. It's not so bad. So every time you increase k, right, that adds another 10,000 dimensional, or it depends on your application, vector to the problem. It's not so bad. Really, the computational burden is mostly the number of documents, right? Because if we back up a second, so although there's a lot of words in k, we could probably really delete a lot of them because think of it as useful words in the dictionary for these kinds of tasks, right? We could probably really pare it down to like a few thousand, right? But as you increase the number of documents or allow longer documents, right? The real bottleneck tends to be here, right? There's a lot of word connections, and so you have basically the algorithm has big loops over n, d, and k, right? And so it scales not terribly in them, right? But we're talking large numbers here, right? So right, if n is, if you allow like 1,000-word documents and you have 1,000,000 documents, right, that's 1,000 times, we're talking a lot, right? So yeah, the scaling isn't bad, but I mean, the caveat is, of course, right, if you have really large things, I mean, these are just big for loops.
So once you create your array of words and you want to pare it down, right? Now, what would you use to optimize that? So
Yeah.
you got the array how you want it. You got trying to figure out, okay, what does it mean? You see some things that may or may not fit. You get some other things like that. And so, okay, now I want to pare this down even more to fit the category or to validate the category.
Right. So you can use the same kind of approach that we talked about before, right? Yeah. So you say you run this thing, and you're like, oh, right, I get some good categories here, but these other ones, I don't know, they don't make so much sense, right? So what you could do is you could add priors, right, for the categories that you think are good. Right, so prior, prior probability distribution over alpha and eta, right? So the map estimation thing, like I think there should be a topic that's basically about sports, right? And then you could rerun the algorithm to sort of refine the other information. Again, right, you end up in local optima, so rerunning the thing multiple times could give you different answers. Right. But if you want to sort of keep some categories, right, you could add a prior that sort of biases you to keep getting those categories back, right? I mean, you don't necessarily will, but like it would help, right? And you can sort of explore the space of other, sort of the permutation space of the other local, optima for the other categories, right? So that's one way to do that. Yeah, I mean, so with a lot of these things, especially with like non-convex optimization, there's a little bit of art to sort of rerunning the things a couple times, and for a lot of things, picking good starting points. Right, picking good starting points for the parameters can really increase the quality of the solution. There's no real hard and fast way to do it, right? Again, it's probably really going to depend on your application and what exactly you're trying to get out of it. Other questions? How are we doing? So, I think that's mostly what I wanted to. Covers everything I really wanted to say about this. It might, since we have a few minutes left, it might be worth pointing out a couple other extensions that I think are interesting. So I mentioned the authorship extension. There's some other interesting extensions that come up in practice. There's something called supervised LDA. So same kind of model, right? Topic distribution over models, but in addition, every document has some other observed value associated with it. So where this might be applicable, let's say that we're Amazon, we've got a bunch of product reviews, right? And I want to do some, basically text analysis on comments sections, right? So every comment section, of course, is a bunch of text, right? So that's the observed words that we already have in the model, but it also has an associated rating, right? And maybe I'm really interested in predicting rating from text, right? It's a reasonable thing to want to do. It's an important application. I care about it, right? So then I could extend the model to have this additional observed variable, which is the rating. And now it becomes sort of a semi-supervised problem, right? I'm really interested in predicting this rating, but I also don't know how to break the comments into different topics in order to do the prediction, right? So I sort of do it jointly, and things like this are called supervised LDA. Basically, you can just imagine like there's an unlimited number of extensions like this. The algorithm doesn't get so much more complicated when you add these additional bells and whistles. It just really depends on what kinds of things you're trying to fit, right? What kind of information you're trying to extract with your data, Lots of things can be put into this framework or just slight variations of this framework. However, if you start going to slight variations, you're going to have to code it yourself. So just caveats there, right? Find some students or something that can debug the whole thing. Yeah. Other questions about LDA? So you get a chance to play around with it on the lab. So you'll just use a built-in toolkit. So you'd have to do a little bit of data pre-processing and then run through LDA. You'll get to play with the different parameters like K and see what kinds of things it's giving you back for topics. It turns out this is super, really, I can't emphasize, it's really, really useful in the social sciences and the humanities for really extracting patterns from data. Right? It's much more useful than clustering because it's sort of there's a meaningful way that it's trying to select these topics. Right. Okay. Well, if that's it, I guess let's take a coffee break again. There's a quiz, right? Just short survey. Hopefully, all the answers are correct on the on the quiz this time around. And again, just to make sure that you sort of got together the high-level points. I think LDA is kind of it's pretty intuitive. Though, like I said, you can play around with it and see how you feel.